Okay, perfect. So everything is on. I hope you can hear me well. So let's start. So thank you everyone to join. Probably more people will join soon in a few minutes. So I will make some small introduction from myself. So my name is Marcin Ruta. I'm the power system consultant. I help companies with AFRA risk assessment, and also it's part of the power studies I'm doing. And today webinar is focused on AFRA risk assessment and precisely on scope of work, how to define it, what it is. So that's what I would like to cover today. We have 30 minutes, or at least I try to keep it under 30 minutes as a presentation. So let's keep it short. So that's why we start. We don't really wait that long. Also, there will be a 50 minutes plus minus Q&A session. Depends how much questions you have. And so please use the chat box on the right side in Teams to write the questions. I will just scroll it down later to find out the questions and answer it in the Q&A. Anything else? Okay, I'm recording this, so I will share the video from the webinar recording later on my LinkedIn, and this will be on the YouTube, but it's not available. So if you would like to, you don't have it link or something, just let me know. I will send it to you. It's no problem. So let's start. I hope you can see the pointer here also. So that's the short agenda for today. So this is a short reminder from last webinar why we actually do those analysis, why we do AFRA risk assessment, the core work, which is the scope of work now, how to define it, shortly about the report content, so I will show you examples around it, and then we have a Q&A session. Okay, I see. If something will be wrong, just let me know on the chat, but I see that everything is okay. People can see my presentation. So let's go on. So actually why we do it. So the easiest way is to show you the video again. Some people saw it probably on LinkedIn. And that's it. So I showed this video because I want to show you, okay, that's what can happen. Now it makes a difference what kind of PPE you wear, if you use it in the right way, if you follow the right working procedures and so on. So this is self-explanatory, but as a small comment. You will always expect damage to installation. 99 on 100 cases, you will see some kind of damage. It can be bigger, it can be smaller, but eventually there will be something. There are some solutions to avoid it, but it's part for the next webinar for the mitigation, where I don't want to dive that deep today. What we would like to avoid, and that's a warning, there will be some injuries shown now. We want to avoid damage to people. So we would like to do everything to avoid such situations when people end up in the hospitals. And this example is from Science Direct article, which I found. It's more medical focus, but that was 25-year-old guy. He was working on the generator, 1.2 kV, and that was 16% body burst because he touched some terminal box, and then he ended up on 4 months in hospital, and then 1 year of very intensive treatment. So, and that was only 16%. So we would like to avoid this, and to avoid it, in NFPA you can find hierarchy of controls. So that's very nice metrics to show you how to control the risk. And that's perfect because we start from elimination, most effective methods down to PPE, the less effective, so-called. And so we have multiple steps, and I keep it as a reminder here, as a short introduction. And I like to add on top of it identification, which it's not exactly, but for me it's very easier to understand now. And this is how to control, maintain the hazard. And identification is a process which shows you what kind of hazard level you have. So once we know our numbers, we can go further and do everything with it. And if we do our scope properly, if we define our scope properly, scope of work, then most of those topics supposed to be covered and should be covered. And if not, they kind of indirectly are related with AFRA's report. So if we do everything nice way here, then a lot of decisions we can make based on the AFRA's results, AFRA's report. And I'm not saying this because that's the topic for today. So what's the simple goal? And I know not everyone is technical, so I try to keep it simple today, as far as I can. So technically speaking, so we have 3 steps. Generally, we have electrical systems. Is a factory, utility, whatever it is. So that's electrical system. So simple steps. We have to model it, so create the electrical model. We have to run all the required studies. I'm specifically not saying what it is. And then we have the results, so we have the report. So that's 3 steps we have to follow. Doesn't matter actually how we do it. From the identification process, it looks like this. We have the medium voltage switch as an example here. Medium voltage transformer, low voltage panel. That's part of the model that's corresponding to it. And we would like to identify the energy. So usually in calories per square centimeters, can be joules. We have to define the hazard area. So how far AFRA's boundary, how far the arc can be dangerous for us. So 1.2 calories per square centimeters limit. We have to then select required PPE for work and then provide recommendation for improvements. And the order is not random, it's most in practical way, that's how it works. And I will elaborate a little bit on this later, why we do it in this steps. So when we identify everything, you can actually see results. So this is just a partial results, but you can identify the energy. So now you can select your proper PPE. Maybe you can adjust your previous PPE selection. You can decide for the hardware improvements. You can make some, generally decide what kind of mitigation techniques you will be using, because there will be a difference on medium voltage, on low voltage, depends on the level and of energy. Of course, we have an AFRA label, AFRA training. You can make priorities for the modernization, for the retrofit. So all those things supposed to be possible when you do a proper scope of work and proper risk assessment. So if you are here on the scope of work, very simple. I show you 3 steps. This is a bit more than 3 steps in practice. If you follow probably on LinkedIn, then you probably saw this chart that I showed before. I'm showing this because there's a lot of work that I do that customers actually doesn't see, but it's good to understand it. So what this beautiful yellow cloud is all my work. Generally with the customer, we always have the discussion and they have to have defined scope of work. Sometimes I help with it, but generally speaking, that's the part where the customer is most involved. Also in the data collection, usually the customer is involved because it's helping with it. But so we need to collect all the informations. And we'll talk those steps later in more details. Of course, there is a system modeling, there is all the calculation that I will mention, and I said before, I have to do. I have to then review all the results, rerun all the calculations again. So we do it twice, wrap it up in the report. So everything is clear for everyone. And then we go to AFRA's training, introduction, so report presentation, AFRA's labels, things like this. Everything that has to be done to explain what we did and to make it clear how to use it. And finally, we just do the follow-up. So once we have the system, we have to maintain it, model, so keep it up to date. And in order to do it, there are multiple standards actually to follow. It's not the one even. So it depends on your location, of course, you follow different one. As a base, we always look on the NFPA 70E. That was latest revision in 2021. This is directly linked to IEEE 1584 because it's referencing it as a guide for making the code. So this is the electrical safety in the workplace as a guide standard for it mainly in US, let's say, but it's worldwide used. And IEEE is a guide how to make AFRA calculations. And there is also IEEE 1584.1 from 2013, which is a guide how to specify scope of work. So that's precisely what we are talking today. This is a bigger document, and I will show you an extract from it. And of course, we have a Canadian standard, which is slightly different from an NFPA, but it's very good, let's say from practice point of view, if you want to follow, good to know. There are some technical reports from Electrical Power Research Institute. If you go for higher voltages than 15 kV, we have OSHA, we have DGUV in Germany, 203.077.078, depends on language. And there are other solutions mainly made from software providers like ETAP, for example, when they have their own calculation for AFRA, based comparable with ArcPro, for example. And also we have a IEC, a bunch of support standards, British standard IEC, VDE, and so on. That's purely for calculations. So just to give you an idea what's happening in the background. And so if we go to scope of work, so that's what I would like to focus today. So generally, you know how to define scope of work. First thing first is always drawings. So we look for the single eye diagrams, paperwork, whatever it is, just to have an idea how big the installation is, how complicated it is, what kind of operating modes you can have. And that's situation important because it all has an influence on cost, generally on work and cost. But also how complicated your system is, it makes a difference from AFRA calculation point of view. Then we also have to define the bottom level. So we always start from the medium voltage level or high voltage level, depends what you have, and we go down. And go down means that by IEEE 1584, it's 2000 amp short circuit level at 208 volts. This is, let's say, more American ANSI style. The problem starts when I ask for it because no one knows exactly where they have 2000 amp short circuit prospective short circuit level available. No one knows really. So from the practice, we always define the bottom level down to 63 amp three-phase miniature circuit breaker, like the one you have in-house, installation style, or 100 amp fuse at 400 volts level, because usually they are three-phase. So that's the typical ending point or starting point. It depends from which way you're looking at it. And I have a project when I go actually much lower, down to 16 amp, because it can happen, depends on what kind of protection you have. So we go sometimes much lower, depends on the customer requirements that's happening. But as a scope of work, it will be like this, as a base. And why it is important. That's the goal for today's webinar. Every analysis, actually everything is prone to low quality level of execution. So the same is for the AFRA risk assessment, especially when as a customer you are not aware of or you don't have a deep electrical knowledge in this field. So you don't know if this is okay or not. Sometimes the customer has incorporation, but as the big company, when they have people which are aware about what's happening. Generally speaking, if we have a properly defined scope of work, it's aligned with IEEE 1584.1 requirements, and those requirements looks like this. We have to do data collection, and usually it means size visit because we would like to have the information from field, not from paper, and we also kind of involve staff in this process. Modeling, it's like try to avoid Excel or hand calculations. It's not because they are bad, it's just because they will provide some limitation for the modeling and for the complex systems and the future use of this model. So usually you will find out something like ETAP or SKM, Easy Power, maybe Dixieland and things like this. From electrical studies point of view, and that's important, we always start with the short circuit study. So we have multiple scenarios, configuration depends on the system. The last project I have, it was up to 16 scenarios in one project. We then do equipment withstand evaluation. You can call it different way, like the short circuit evaluation. Simply, we have to evaluate short circuit withstand rating of breakers, switchgear panels versus calculated short circuit current. So we know that they are designed proper way and selected in proper way, so they will not break. Selectivity analysis, very important point, because that's part which reviews possible problems with the protection of your system and allows for improvements. That's a very critical point, we talk about it. And of course, AFRA risk assessment, our main goal here. So we want to identify the hazard level. Sometimes you can see a load flow or harmonics, but they are optional and usually driven by the existing problem. So that's why the customer is coming back with it. They know there's something happening and they would like to check it as part of the modeling. Of course, recommendations. So we actually do this twice. And we provide a recommendation how to improve, how to mitigate AFRA. And that's, I say, on technical level. So provide settings, different hardware solutions. That's what I mean. AFRA labels, of course, AFRA training. Like in US, sometimes this is combined with electrical safety training. In Europe, we do it slightly different, but because the part of it is combined outsource or by official bodies, depends on country, of course, and the report to wrap it up. So all the input data. So let's speed up a bit. So when we talk about data collection, of course, if you are not aware what it looks like, it generally means I collect all the information like transformers, cables, bus ducts, especially protective devices settings, relay CTs, whatever you have, UPS data, battery packs, power and voltage, things like this, and especially configuration of your network, all configurations of your network possible. It's important because we need existing data from site, not from documentation, unless it's verified, like sometimes in oil and gas offshore, where it's not changing very often. There is always difference between paperwork and what we collect from the field. And the site visit also allows for doing some kind of visual inspection, most of the time from the shock hazard point of view. And site personnel will be involved, which is very good for learning point, because we try to show them what we're doing, why we do it this way. Sometimes they don't have to come back to the site anymore. They know what they have to do. And just an example, because I don't know how to show you the data collection process. I just make a lot of photos, collect the papers and things like this, drawings. So that's more or less how it looks like. I see some questions, so feel free to ask questions on the chat. I will go back to it at the end. So we have the digital model, of course. Digital model means that we use the software most of the time. That's because of productivity, quality, and everything else. And depends on software use. Generally, this is a base for all analysis we do, AFRA, but also everything else. So that's important. Most of the time you will see those three. There are more, there's no problem with it. If you use the right software, you can, depends on the software used, there are some certain capabilities. Sometimes they don't support IEC, sometimes they don't support IEEE, sometimes they can limit the future use of the model if you want to do like motor starting or transient analysis, everything else. So then you have to remodel things, and also additional costs. They have to allow for multiple scenarios, so for comparison of the results. When you won't like to provide the recommendation, you have to have a chance to show it in the easy way, what if scenarios. So digital model looks more or less like this. This is from SKM, this is part of VTAP, and so on. Doesn't matter really what kind of software, it has to be clear and easy to use. And I'm just talking from my perspective because I'm using it. As a customer, you don't really care about it, but it's important also for you. Sometimes if you decide for something else, you got some Excel files, things like this, which you cannot use in the future. From short circuit point of view, of course, short circuit is a base. It's not that I want to do it short circuit study. I have to do short circuit study when we do arc flash, because arc flash is a combination of few things, arc flash analysis. It's very important from point of view when we actually do the design. So, and design means, okay, that can be new site when we do design and we have to run multiple scenarios for short circuit study. Like I ran recently, I think 6 for one scenarios for one side of the data center. And this is purely made by design. So we want to verify if the equipment is rated properly, if they withstand the short circuit current, because that can be also the reason for the fault on arc flash to escalate. If the equipment is not properly rated, will break, will just have mechanical damage. It can escalate to fire and overheating, whatever, and then to arc flash. So that's why we actually do it this way. Of course, depends on location. This is ANSI or IEEE or IEC, like VDE. Sometimes depends on requirements. Depends on type of installation, like marine. Is it AC or AC/DC systems? So important point to mention is that we not always look for the maximum short circuit current. We look for the worst case short circuit current, which sometimes, like from arc flash point of view, which sometimes means minimum current with the worst network configuration. And that's important because you cannot do assumption that we take, that we have 15 kiloamp and we take 55, 60 just so we are on the safe side. This doesn't work like this. That's counterintuitive when you talk about the arc flash. And that multiple scenarios are important. And just an example, this is like kind of summary from multiple scenarios, something on the single line, like this is like a small part from IEC standard, the graph. And I want to show you the example, how it looks like from testing. That's what we discussed. So this is present the cable holders, different cable holders. And you see a lot of force is happening. You can see it here. And if this thing is not designed properly, and you see the difference here versus this, and if they are not properly rated, not properly designed, in this case it means the spacing because of the force, then you can end up having something like this. So if the system is not, then it will not withstand the mechanical force, and that's just on cables. And then let's say like this. So that's part of why we have sometimes short arc flash currents, arc flash accidents. The next step is very important, is selectivity analysis, and that's the first. What is selectivity or protective discrimination? Good word, I think, that works for most people is cascading operation. It doesn't work always like this, but it's a good word. We would like to check that protective devices works in coordinated way, which means we verify the settings of breakers and relays for proper operation. So they have to work as fast as possible, but on the other hand, they need to have enough intervals between each other, so they allow for interruption only faulted blood, which is called selectivity. In practice, it makes a very big difference, because if we have a small fault somewhere, and I'll show an example in a minute, if we have a small fault, we would like to be sure that the installation will be will be tripped or switched off only in this area. So we don't want to have half of factory to go down. And there are several ways to do it. Depends on the protective device you have on site physically installed. They have a different settings, they have a different functions, they have a different communication sometimes, which can be utilized to do it. And from usually the selectivity is also the starting point to provide any recommendations from safety improvements, from arc flash point of view, and so on, because it allows now to show you everything what's happening in the background. And usually also this is the first reason why this thing is ignored in arc flash studies. That's why it's excluded or is treated very, very on the minimum level. So it should look more or less like this. So just to give you an example, that was not selective area, they are both identical. That's the selective area. And I just want to show you that, okay, I don't know if you can really see it here, but this is touching, this is touching, this is touching. Shouldn't work like this. We have a situation when the main breaker can trip for the downstream fault. We don't want to have it. So when we adjust it, we just keep it. Transformer on the safe side can be lower, but there was limitation on the relay. And the low voltage breaker is off, but we have enough time separation for it. So that's from selectivity point of view, that will be good operation. Probably this will be making arc flash a bit worse, because there is always compromise on it. And usually you try to highlight it somehow so people can see what you did, like existing, recommended, so why we did something, give some comments. So I would say I do it this way because it's very easy to see that something was changed. And just to give you an example, I don't know how to show it, but that's a blackout in Manhattan. Ta-da, that's what it is. But that was 73,000 customers without power for 5 hours. And apparently that was a transformer fire that led later to malfunction operation of relays. And for Con Edison, I think it's still ongoing, because they don't have this fine, I think, yet $25 million. It's ongoing. So our goal, arc flash risk assessment, that's what we would like to achieve here. So very important point is that we do always existing situation. So that's what it is at this moment as a base. And then usually we go to the recommendations. So we try to recommend some improvements based on settings, based on the hardware solution, depends what was agreed with the customer that we can do, and provide recommendation situation, which is second set of calculation. And that's important because what I said before, we identify the energy, we select PP, and then provide recommendation. And that's it, because between the existing situation and switching to recommended situation, making all the necessary hardware and field work, This sometimes takes months or years. So we always go with existing and then we switch to recommended, usually this way. Important step here is that, okay, if we go recommended situation, we provide possible improvements, but also limitations of our system, which means that sometimes you cannot do anything with your switchgear and it will stay like this, 40 calories, we cannot improve it. It's very rare, but sometimes it happens. And this is also the second reason why this is ignored in AFRA studies, providing these recommendations, because it requires a bit more knowledge. You have to provide the base, you provide the recommendation, identify the situation, show the difference and why. You can show the results in multiple ways. I like to show it on the single line if possible, and with the color coding, so it's very straightforward to see. You know, in a visual way. You always will find it in the table form. I like to add this color coding to it because it's also in the visual way shows you the amount of things that's happening. Personally, I like it. And if you look on the IEEE, you look also on the report content. So generally there are some requirements that we have to deliver. Usually it means all input data and modeling assumptions, which means, okay, if I select different views, if I select different breakers and things like these cables, that it has to be mentioned in the report that we did some assumptions like short circuit power. All the input data, which means, you know, the list of the cables, whatever we collected, model it, you can do, that's why we use software, actually you can do it very easily with it, with all the calculation results for inside short circuit arc flash time current curves, those graphs that I use for protection, low flow harmonics, depends what we do really. We have to show it because sometimes there is on the other side, there is a person like me in the big corporation, which is checking my work for quality and they say, okay, Martin, that's okay. We accept it, good. Not every customer has it, but it has to be there. Sometimes you have to look for the second opinion. Selectivity analysis summary with comments, and that's a good practice. So actually you can see as a non-technical customer sometimes the difference why I propose something like this. The same is for the AFRAs. So we have the labels for the existing at least. And also for the AFRAs results, we do the same. I do the comments. Okay, that's what we did. That's why we can improve the situation with the recommended settings, but or with maintenance mode, fiber optic protection. Depends what was agreed with the customer on technical level. And then the recommendation part. So the same things like all the results for this and this. We try to from why it's important, but I try to always highlight the conclusions, don't bury it in the report. So you have to have chance to find it very easy way. And that's because I myself, I did reports which were 500 pages. I saw a few thousand pages reports, and that's conclusion was that no one was reading this. It's very hard to read. So we try to keep it simple. From a recommendation point of view, so you would like to highlight it, make it clear what we did, that was existing, that's recommended. So I would say that's very easy to compare, and sometimes customers can have good ideas. Okay, we would like to exchange the switchgear, stop it, don't do any recommendation on this. And again, good practice is to keep the report easy to read. It's technical enough. Let's make it easier for others. And I can show you an example from mine. We will not go through all of this because we are ending, the time is almost at the end. So we have a main report, some appendix A, if you can maybe see it here, which was existing, and appendix B, which is sometimes bigger or smaller, for recommendations. And just to give you also some ideas, if I do some recommendation, if I have very like more than few scenarios, then I try to highlight all of them and then show the difference. Depends on the software you're using. And then you can see the comments, like, you know, no real improvements possible. Maybe you need to go with the maintenance mode settings and so on. So breaker has some limitations, things like this. So you can actually very clearly see what was happening and why we have this. And again, you can drop it on the single line. So I like it because it's very visual way of showing. And some example now after AFRA labels. And I have this slide not without the reason. So we have the, like this is more IEC way that I'm using because we have some different shock hazard situation, not situation, the distances. That's very common the way on ANSI level, let's say. Sorry. But there are like at least 40, 50 ways how to make the template of 4 labels. And that's the former historical way. And I keep it because we used to use word danger. I don't use it anymore. I use warning. And there was like this word no safe PP exists when we go above 40 calories, which is not true. And IEEE actually removed it a long time ago. However, some customers are still insisting for it. Usually saying that it's not a problem to keep installation below 40 calories if we do recommendation. So that's why I actually do this part also, so make it safer. But it's relatively easy and not to end up with something like 70 calories and leave the customer with it. Enjoy danger, you cannot work here. We don't use actually this thing because you can buy PP up to 140 calories now. So technically you can protect yourself in this situation, so there's no need to use such labels anymore. So that's just as a, let's say, information here. And so we end up, thank you for your attention now. Now we have a Q&A session and you can ask your questions on the chat box and I'll answer it. So I saw at least one question here. Let me scroll it. So Chris asked, IEC 60909, IEC 6363 is that they cover short circuit fault calculation but do not extend to AFRA instant energy calculation. Hence, we typically revert back to IEEE. Do you know if there is IEC standard guidance in development to provide more IEC focused guidance for arc flash incident energy calculation? So yes, it is. That was the one that I mentioned, DGUV 2003077. That's the approach from let's say European side. Maybe just to give you a bit of comment behind it. IEEE is used, so you can use IEC 60909. There's no problem with it. Technically, you can even use IEC 6363 for marine. Just most of the time, it's not used for it. We use 60909 in marine also for AFRA calculation. That's good enough. And DGUV is just not like, let's say, not the European way. It's just the box method test way. So it's a bit more, but we have ATPV, we have a box method. And for ATPV, we use IEEE 1584. And for box method, we can use DGUV 2003077. But generally, this is working only in Germany for a moment, and 99% we use IEEE 1584. That's because we have ELIM. So I can send you a bit more explanation because it's not an easy question. If we can access the recording, yes, so there will be a recording, and I will send the link on LinkedIn. And I can also send it directly to people who just give me a hint on message or email. I know there are infrared monitoring systems installed within the switchboard joints area to monitor the heat spots to identify early failure. How you see such method beneficial to AFRA study? So technically it doesn't have anything with AFRA study, so it will have no influence on it. Influence it will have on the risk assessment, or maybe not even. It will not change anything. It will just allow you to identify early stage of failure, which is very good to have. So you, in case you see that there's something happening, pending failure, that's how we call it, you don't send people to work. So you reduce the risk, or you actually avoid the risk. But it will not have any influence on calculation, unfortunately. So generally the arc flash risk is for calculating the energy of arc flash explosion to build some precaution how to build the mechanics of the switchgear and which clothes the maintenance people should use to be safe when working with the switchgear. It's not how to build the switchgear. Well, technically it is, but we'll go now in FMEA calculations. That's a different story. You look on the arc resistant or internal arc classification. So that's when we talk about the mechanical of the switchgear. And from arc flash risk assessment, that's what we do, arc flash calculation, is not purely to tell people what kind of clothes, what kind of PPE they have to use, is first to reduce the energy. And sometimes we do it so good that they don't have to use any specific arc flash clothes. So to keep energy below 1.2 calories per square centimeter. So it's more about to identify the energy and then to decide what to do next. You can use internal arc classified switchgears for it, for example. But there's always some area where you need to have PPE. You can use arc resistant on low voltage switchgears also. But also you can use different like arc quenching, fiber optic arc detection to make it to limit the energy. So usually this is the identification process which allow you to decide what to do next. That's from Edison. For an outdoor application, and there is an outdoor after X. I don't know what this word means, SQChan. How did you assess the AFRA category? That's from Edison. Can you maybe make it more precise? I don't know what the SQChan means. If you maybe can make it easier for me, please. Any requirements of power distribution transformer? Okay, that's Alanka, don't do it. It's an advertisement. I will share the webinar later. No problem. Chris, for there is risk assessment involved. How do you generally recommend approaching AFRA studies for medium and low voltage switchgear control that has undergone the classification? In theory, the operators are protected around this equipment with all those and covers in place. Would you only recommend an AFRA study when accessing the equipment for modification, maintenance when the equipment is live? So once we do the study, we know the result. It doesn't matter if your doors are open or closed. If you have internal arc classified panel on medium voltage, let's say, we verify if this classification is in range of what we calculated. So if, let's say, if you have 16 kiloamps 1 second, if you have 20 kiloamps 20 kiloamps, it doesn't matter what time it is. Now we say, okay, it's not fulfilling the internal arc classification, but most of the time it is. So in normal operation, as you mentioned, it's okay, it's safe. So, okay, thanks. It's safe. So this means that you know the results. I did the project recently like this for 20 kV. So we know the results. We know that there was internal classified. Now, if you work live, so you have to do voltage testing, for example. So or absence of voltage test. Let's say you have a old switchgear. So for now, you have to wear your PPE, do it, drop it, and then you can work. This will be just included because usually medium voltage is the first level. So we always include medium voltage for calculations. And that's very easy. I hope I answer your questions. So there is nothing special in approaching this. Okay, Edison explained another door inside. So if you have outdoor application and there are doors after the doors, this means, okay, we treat it as a cover, let's say. Depends on what kind of, this is more about the labeling now. Let's say we did the study. Now we have doors. We open those doors. We have the next door, which is, let's say something is after it, something live. So we treat to the information to the second door. Of course, there is an influence, mechanical influence of the doors in between, but for a moment, there is no way how to calculate such influence. So you can make an assumption that the arc can stay inside, but you don't know it for sure. Depends on construction now. We'll have to do FMEA calculation just to find out what the force is and so on. And this is very, very, very time consuming and expensive thing to do for one switchgear. So normally you will treat it as there are no doors. We try to calculate just purely without the doors what kind of energy it is. Just the fact that doors are in place, they will be treated as a cover. So if you're just approaching those doors, then you don't need any PPE. If you are opening the first doors, but you are aware that there are second, you still don't need a PPE. If you open the second door, now you need the PPE because you are accessing, let's say, live equipment or whatever it is behind the doors. So that will be the approach from this perspective. Oh, thanks, James, for the precision. Maybe I can elaborate a little bit on if you have a new switchgear and internal arc classified, because that's very common. So that's what I hear very, very often. If you have there is a new switchgear, so we are on the safe side. Technically not. For calculation, it doesn't matter what kind of switchgear it is. Is it new or old? Of course, it makes a difference. because you have a bunch of new solutions that which you can prevent from shock hazard point of view and things like this. But in case of fault, if your switchgear is not internal arc classified or arc resistant or for low voltage, you cannot make an assumption that it's safer. So that can be perfect old switchgear, 40 years old, pure best maintenance possible, and it will be okay. And it can be brand new, which will be generally the same situation if you do one-to-one change. And there will be no difference for AFRA calculation, maybe small. And so I always try to explain the fact that something is new, like with the car, doesn't mean that you cannot have an accident with it. So it makes it better, it makes it easier, but if you hit 100 kilometers per hour with the wall, okay, it's the same effect almost. And so you would like to keep it safe. You still need to identify the energy. The difference between new and old is that you can maybe utilize some better options, better functions, better breakers, can be faster. So in theory, in practice, it should be slightly better. But if you create a fault, it's still an explosion. Or depends what we calculated it is. So you have to keep in mind when you are specifying your switchgear, you have to keep this thing in mind. How about air insulated open rack type distribution board? Should those be banned from any projects? Would there be any regulation in soon? I don't know about the regulation. It's hard to deregulate something that is existing. Yeah, hard to say. They will be treated more or less as open air, so it's actually could be less dangerous in calculation, but hard to say to you, Michael. This will be if you deregulate something, you have to force people to change it, and it's a lot of money. So I don't think so. Chris, I understand. Okay, I understand this is a German standard. Do you know if there is a plan to devote an overriding IC? Not what I know. I don't think there are any plans. Actually, IEC is international, so it's not that we have it in Europe only. IEEE is also international, and from my perspective, there is no need to make a double work because IEEE is referring to IEC PPE testing. So we have 61482, which are both OpenArc, ATPV, and box tests. They are both IEC testing methods. So we are selecting our PPE based on IEC tests. And IEEE is just the way how to calculate the arc flash, which you can, I kind of make it Europeanized way, which we use IEC, the smaller gap distances that we use in Europe. And that's it. It's like almost, I don't know, they have it in 30 years in US, and from IEEE perspective, it's also a very long time. So they have very good data, and I'm very happy to use it. And I use it for more than 10 years, but people use it more than 20 years in Europe. And I would say it's a very comprehensive method. If there would be any IEC work, it would be very welcome. The problem is, from my perspective, that they always align more ATPV or box method tests, which I don't know why, because they are both IEC. Just I know why, but because it's the PPE manufacturer, but that's other story. Do I know what my next webinar will be based on? So my next webinar I'm planning to do on mitigation techniques. So to talk a bit more about how to mitigate arc flash in technical way, like protection settings, fiber optic detection, using some pros and cons on internal arc classified switchgears and things like this. So that's the next one, and I hope I do it in like something like 2 months. I hope, depends on my workload. So we still have some few minutes left, and if you have any question, you always can you can always message me directly on LinkedIn. You can always send me the email, the invitation that you received. If you made it back, it will send directly to me. So that's no problem. I always try to send answer the question as far as I can, or maybe call. It's easier. And let me just check one thing. And of course, I hope I answered some of the questions you got, and I hope it was good. So any feedback is appreciated. If you have anything, you would like to hear or improve, just let me know. And so I think that's it for today. Thank you very much. Let me stop recording.